Hey kiddos, in today's video we are going to talk about resonance, but in a different way than what we talked about resonance before. So I think that everyone has a pretty good clue about how to draw resonance structures and what they're for and how they sort of represent a hybrid between things, and there's a delocalization of electrons. But one of the things that we didn't really discuss is how to know whether or not a particular resonance structure was better than another structure. And so what we're going to talk about today is how to draw some resonance structures and then to evaluate amongst those resonance structures which things are the most correct resonance structures and which things are not really an allowable resonance structure at all. And so there are going to be three quick rules that we're going to talk about for this. The first one is one that you essentially already knew. Okay, so the first rule is to minimize charges. And we knew that anyway because we talked a little bit about it probably in Chem 1, and certainly if you took AP Chem or College Chem, you talked about formal charges. One of the reasons that you did formal charges usually was to establish which of a couple of possible structures that you could have drawn something was more correct. And so that's also going to be true for resonance. And so to do that, we're going to draw our friend acetic acid here. So we've got our acetic acid structure here. Acetic acid, obviously one of these things that lends itself well to resonance. We have electronegative atoms, we've got some lone pairs, we've got a double bond here. And so you can already sort of see that we can do some shifting of the structure. And so let's get to it and draw some possible resonance structures, okay? So we can definitely draw one there where we have the double bond up here and giving us another lone pair. So if we draw that structure down, then we've got this scenario. Now what that automatically sort of does for us is that it tells us that, hey, we now have some formal charge type situations, right? So we've got a negative formal charge up here. We've got a carbocation down here. That actually isn't the only way that we could draw that structure. We could also take and shift and move here as well. And so that would leave us then with a third possible resonance structure where we've still got our scenario here with the three lone pairs. Got a double bond here, so again sort of showing that we can shift this in multiple ways. Okay, when we get that scenario drawn, then again now what we have is we still have our negative formal charge on this top oxygen that has the extra lone pair, but now we've shifted that cation, that positive charge, over here. So let me draw some quick arrows there so that we know that that is a third resonance structure. And so we've got three conceivable resonance structures that are possible here. Now, just knowing what you already know about formal charge, the minimized charge thing makes total sense. It says, hey, this particular configuration has no charges on it. These two are possible structures. In other words, there could be possible shifting. So these are okay, like these are plausible resonance structures. But this is the best resonance structure because we have thoroughly minimized the charges. In fact, we don't have any formal charges in this, and everything's still fitting the octet rule, still fitting that stability that we were looking for there. Okay? So we want to minimize charges. In particular, we want to avoid something that we're going to show with not just acetic acid, but with the acetate ion. So let me get to that. So just so that you guys are clear about what's going on here, I'm going to remove the hydrogen off of each of my acetic acids to get to the acetate ion. I've already done it for these two. I want to make sure that you guys can see what's happening. Remember, we're going to remove the hydrogen. So I'm going to remove the hydrogen. That then is going to give us another lone pair here. And of course, as soon as that lone pair comes in there, then that gives us a negative formal charge. That makes pretty good sense. It's an acetate ion, right, with a negative charge. So we sort of can see that. We can see that again here. Even this one would have a -1 overall charge, which would meet our acetate ion. Okay, so we're trying to minimize charges. So what you can see here is that these two structures both have the -1 that we would anticipate from an acetate ion, and that's the only charge that they have. This abomination over here, essentially, we've got three formal charges on three contiguous atoms, no less. And essentially, anytime you have more than two formal charges drawn on a resonance structure, you could pretty much throw that one out. There's one exception, that would be a nitro group. And because of the way the nitro group is set up, that's going to allow that three charges to happen. But outside of that, anytime you draw 3 formal charges on anything, you can pretty much just automatically kind of grab that one and circle it and say that that one is not valid because too many formal charges. We're going to minimize these things. And so these two instead are going to be our relevant resonance structures in this particular case. Okay, so that was rule 1. Okay, so rule number 2 pertains to electronegative atoms. Now, since they're electronegative, what that would sort of mean is that they pull electrons to themselves. They sort of have a lot more stability or a lot better chance of having negative charges than they do have positive charges. They can have positive charges, they can have a cation, but for that to happen, they have to have a full octet. You cannot create a situation where they do not have a full octet. And a corollary to this rule would be that the most stable situation is going to be where everything has an octet, so that if the charges are equivalent, or at least they're close to one another, the formal charges, that what matters then is, hey, does everything have an octet? That's the only way that electronegative atoms like a nitrogen and oxygen can have a positive charge, can be cationic. So if we look at this example here, we can say, hey, this is our structure here. Okay, so if we switch that down here, we get our resonance structure. That essentially is going to pull that positive charge up onto the oxygen, which again, doesn't always happen. It's possible, okay, and you've drawn a few things like that, but doesn't always happen. It definitely is happening in this case. We're okay now because we've got the positive charge on it. It has a full octet. And perhaps even more importantly is that we've gone from a situation where this carbon right here at this point did not have a full octet. Okay, this carbon right now, as of right now, has 3 bonds. It's got 6, and so that's what gives it the positive. That's not the situation that we want that carbon to be in. We want it to have the appropriate number of electrons that it should have. So instead of the sort of 6 and the positive formal charge that it's left with now, over here it has 8, oxygen has 8, hydrogen has 2, everybody else has what they have. And so this is going to lead us to say that this one is more significant or more relevant. Okay? I would probably say more significant, but since I started off with relevant resonance because I like the alliteration, we'll say more relevant. But more significant, this would be the more significant of these two structures. And again, these are both okay. These are both valid resonance structures. I didn't go 3 charges or anything like that. Everybody's got an octet here. This still has an octet, but this is going to be more stable or more relevant or more significant because this carbon now has an octet, as does everything else here. So let's look at one more example of that just so that you get a good handle on that rule. So in our second example here for rule number 2, again, we see 2 resonance structures. We've got a carbocation to start off with. We're going to do our resonance here by moving the lone pair. Okay, and again, remember, we're not moving anything. That's back in the other resonance videos. But this lone pair here, that's going to give us a double bond here. When that double bond forms, that's going to take care of that carbocation, and then that positive charge is going to be spread out again between that and between there. And then, of course, if we're looking for which one of these two is the most significant, or to put it in like ACT, SAT terms, which one is the most correct answer, then this would be the most correct resonance structure. Again, this one is okay, this is valid, but this one is better. Okay? Now, does it mean that it only exists in that position? No, not really. I mean, this is still a resonance situation, right, where we've got some sort of hybridizing between them. But what it does mean is that what we would refer to, and we'll do this a lot when we do reactions later, is that this might have a higher percentage of character as being this way than it might have character of being this way. And again, the reason for that is because everything here has a full octet, including the electronegative atom that has a positive charge on it. Rule number 3, another rule where we're essentially trying to avoid too many charges. In particular, what we're worried about in rule number 3 is that you should never set up a situation where you have 2 carbons that both have charges. In the scenario that we've got them drawn up, they're right next to each other, but it doesn't really matter that they're right next to each other. We don't really want any 2 carbons on the chain anywhere to each have a charge. If they do, then we've probably got something that we could find a better resonance structure for. And so this is our initial model here, okay? So we're going to draw a resonance structure. We're going to move this double bond here to give us a lone pair. That gives us a negative charge on that carbon, which again, probably not the most advantageous thing anyway. we're going to take this lone charge from the nitrogen to give us a double bond here. So we've got a negative charge on a carbon. We've got a positive charge on a nitrogen. Everything here has an octet, so that's at least following that basic guideline that's good. Then we come down and we say, okay, well, what happens if I took that double bond back and put the lone pair back on the nitrogen after we did this shift here to give us the lone pair on the carbon? Well, that makes the nitrogen great, no formal charge on it, but essentially what it does is it shifts the formal charge over here to this carbon, making a carbocation. Now again, initially what that's like, this should go into Rule 3 and Rule 2, is that this isn't a real good scenario because obviously we don't have a full octet on this carbon, but also each of these carbons has a charge on it, and that is what we're trying to avoid in Rule 3. So again, this is a situation where we would say that this bottom one is probably not terribly valid, okay, and that this is probably the best structure in comparison to that one, because this one obviously has no charges on it. This one does have some charges on it. Again, probably maybe favoring this, but going to this occasionally, so there's still some resonance there to allow for some spreading and delocalization of that bond structure, which of course is the whole point of resonance. So hopefully walking through that gives you a little bit of an idea of when you're looking at resonance structures and trying to figure out which ones are good and which ones are bad, which ones are relevant, which ones aren't. Hopefully that gives you a pretty solid idea of how to distinguish between them and how to be able to say, hey, I'm throwing this one out altogether. That's too many charges on carbons. That's 3 overall charges. I don't get my octets here, and so that stuff just isn't going to be as valid. All right? Thanks, kiddos.